Edward.
Isn't me.
It is not.
We're flying alone.
Zach. It's not you either. I'm sorry?
They have short hair.
Short hair. Yes.
Are they bald?
No.
Are they wearing a hat?
Yes.
Glasses.
Are they on the right side of this room? Your right?
Oh, that's a really hard question for me. I don't do right and left. Yes. Yes, after thinking a lot about that. Yeah.
Is it the gentleman in the gray shirt with black hat?
You sure with that? No.
Are they an alumni with them?
Yes.
Marshall?
It's not Marshall. He's not an alumni yet.
Is it the person in the front row with the hat on?
No, it's not Marshall either.
Well,
That's
Mitchell.
I'm Mitchell. I'm sorry. It's not Marshall or Mitchell.
Are you wearing glasses?
I already said right, so I can't think of right. Yes.
Is it the person in front of me?
No.
Are they in the third row back?
No.
Is it this guy who's sitting with the
Yes, it is. All right. So we just used a decision tree. All right. So a decision tree. A decision tree takes from the group, you have everyone here, and you're trying to narrow in on an answer. In this case, we were trying to narrow on a very specific answer, not really a bucket. And we asked questions of each thing. So the first one was, are they male? Right? And we took a path one way or the other. Right? And then we got there, and I forget what the next one was.
Short hair.
Short hair, all right? And so we walked that path until we got to an answer that identified, the classification. So that's a decision tree. What's a random forest? Because a random forest is what we're going to be doing. A random forest is, as it's actually aptly named, it is a bunch of trees, right? And we ask every tree the same question, and they all have votes. So in this case, we're trying to decide whether or not to skip a song. So each tree gets to say, don't skip it, skip it, skip it, don't skip it, and we take a majority vote. All right? So why would we do that? We had to have some math in here somewhere, right? So why would we do this? If we had 25 trees and they all had a 35% error rate, and they were all the same, and we asked them all the same question, and they voted, it would be unanimous, and it would still behave the same way and have a 35% error rate. So why would we do this? Well, what we need to do is we need to make sure that the trees are independent. It's not totally true. But what do I mean? Well, I mean they all screw up differently. So, we need to deliberately introduce some error and some randomness into the way those trees are built. And we'll often do that. There's different ways to do it. But we'll often say, okay, you have all these characteristics to choose from. You only get to choose from these 5. Or you only get to choose from this half. All right? And build your tree the best you can that way. All right? So, that's how that works. If they're screwing up differently, we need more than half of them to screw up to be wrong. And so, we go through and we take the probability that each is wrong and we add all that up, and we get 6%. And I know it's early, so I just want to point out that 6% is less than 35%. So when we do this, the random forest behaves much better than the single decision tree. Not used to having an assistant. All right. So, the other reason, now, I want to confess that random forests are a good algorithm. They're not the best algorithm anymore. Usually we're going to use deep learning. We're going to kind of do all these fancy neural nets with lots and lots of data and lots of layers and lots of training. The reason that we didn't do that with this project is because we wanted transparency. We wanted to be able to understand what was happening. We wanted to know why the decisions were being made because we're trying to gain insight into the problem. So transparency in machine learning is something that we're not valuing enough, in my humble opinion. All right, we are building lots of machine learning algorithms that can do lots of cool things, and we take a step back and we have no idea why they're doing what they're doing. Okay, and when we're starting to deploy them in places that impact people's lives, this gets really scary. So you ask the AI why you didn't get a mortgage, and it goes, oh, math, you know? So random forests are a way that we can actually get some insight into why the decision's being made and the importance of various features in making the decision. So that's what we were doing. And now it's my pleasure to introduce Sam, who did the actual work here.
Alright, so the purpose of my research was to essentially create the foundations of a recommender system in the context of music streaming services, specifically Spotify. So what is a recommender system? It's a type of information filtering system that predicts and recommends items that a user may be interested in based on their past interactions, preferences, and behavior. So this is how all e-commerce, entertainment, and social media platforms recommend music. Here we go now. Alright, so since we're using Spotify, we're using their training data. How does Spotify recommend music? So first, they use natural language processing. They use this to parse lyrics, playlist names of user-generated playlists, and they look at web crawl data. So this web crawl data could be from blog posts or just anywhere online where people are voicing their opinions about the songs. They want to know what critics are saying about these tracks and how they're perceiving them. We also have collaborative filtering that they use, so that's just comparing the listening histories of similar users. If there's a user out there that has a very specific, that has a very similar listening history to you and their tastes kind of align with yours, and they are really interested in this new song that you haven't heard yet, Spotify is probably going to recommend you that new song because chances are you are going to like it as well. So they also use raw audio analysis. This is a little bit complicated. They just input the raw audio of each track into a convolutional neural network, which again, very you have no idea what's going on there, but all you have to know is that the output of that neural network is a bunch of numerical features that describe the acoustic structure of that track in a way that maybe a machine can understand what music is. So these techniques efficiently generate tailored playlists, they personalize the home screen, and they recommend new music. But when a user is listening to a playlist that they've created, they already like all the songs that are in that playlist, but they're in a particular mood. So raise your hand if you put your music on shuffle, and then you just skip through all the songs to find what you actually want to listen to. Yeah. So like all of us. Okay. So the problem is,
Nobody trained me for this.
the problem is that when we're listening to lengthy and diverse playlists on shuffle, it's common for us to just skip through the songs until we find the one we actually want to listen to in that moment. But we already like every song in this playlist, so the techniques that I just mentioned, they're not really going to do much in this situation. Now, so some data from Spotify. 48.6% of Spotify songs are skipped before reaching the end. And a quarter of songs are skipped within the first 5 seconds. So, in my research, I wanted to explore the idea of being able to reduce this crazy amount of skips. And kind of explore what if Spotify was paying attention to the tracks that I'm skipping, and it started creating music relevant to my mood in that moment within a session. So our research questions are first, can we predict whether or not the final song in the session was skipped? And when making these predictions, which features are most prominent? So our idea was to see if we could predict whether or not a user skipped the final song in a session. And to do this, we used a random forest classifier. So there were 100 decision trees in this ensemble, each with a max depth of 6, and we used a subset of a Spotify data set. It originally had like 130 million sessions, but that's a little bit too much, so we just used 200,000 sessions for the sake of time. These are of anonymous users, and each session averaged 15 tracks. So 70% of that was used for training, and 30% of that was used for testing. I have on here why random forest, but Dr. Schwartz kind of went over that. So we are really trying to figure out which features are most predictive when this model is making its decisions. And to do that, we use mean decrease in purity, which is just measuring, as we go down the tree and we're splitting the data on each feature, how well is that feature categorizing the data and splitting it into clean groups so that we can categorize it better, classify it. So this is what the data looked like from Spotify, and this is just one session. We have the session ID, the length of the session, and the position of each track. We have track ID, which I'll talk about in a second, and we also have whether or not the user is Spotify Premium, has Spotify Premium or not. We also have the hour and the date of when the session occurred, and of course for each track we have whether or not it was skipped. So if we look at the track ID of the final song of the session, because this is the one that we're trying to predict on, we can put that into the track data set, and here we can find 29 additional features about that specific track. Now, a lot of these come from that convolutional neural network that they use when they put the raw audio into. So we've got duration, that's just the duration, the acousticness, danceability, energy, flatness, and some just musical features like key and tempo, and also balance. So some of them are more vague than others. Like danceability is just a made-up word from Spotify. It's how they measure like how likely someone is to be able to dance to the song. So they're looking at like the tempo, the beat strength, and of course the energy plays a role in that. Also like energy and acousticness, just like how acoustic is this song. There's a numerical feature. But because these are all numbers, we can represent this as a 29-dimensional vector. We can normalize the data, and we can compare it using linear algebra. But before we use any linear algebra, we actually train a random forest just on this data. So we use the track features of each final song in the session, and we use that to train the random forest just to see if there was any correlation between the actual structure of the track and whether or not it was skipped. So this was about like 50% accurate. It wasn't learning at all. That's like basically guessing. So then we decided that the metrics would probably be a very much better way to use the track features. Yeah. Okay, so this is kind of how we've looked at the session. We have the played songs, the skipped songs, and then the final song that we're trying to predict on. What we're looking at here is the most recently played song and most recently skipped song. We kind of hypothesized that the similarity that these songs were to the final song could play a role in deciding whether or not this song was skipped or not. And then also, we made average vectors for both of these groupings. So we have a played average vector and a skipped average vector, which we could also use some distance metrics comparing to the final song to see some things. And then here's that visually on like a 2D space. The song to predict is there in black, and then we've got the played tracks in green and the skipped tracks in red. Sorry. So you can see that the closest song to the song to predict was in fact played. So maybe this could also give us another clue when we're making predictions. Okay. So to summarize what I just said and what I just put visually for you guys. So on the previous slide we had neighbor skip, which was just a boolean indicating whether or not the final song's nearest neighbor was skipped. And then we have man last skip and man last play. These are both Manhattan distances between the final song and the last skip song or last non-skip song. And then we also have man out skip and man out play, which of course is the Manhattan distance between the final song and the skipped average vector or the non-skipped average vector. So originally we tried all these Manhattan metrics with Euclidean distance and the angle between vectors. But when we ran these features in isolation just to see how predictive each of them were, the Manhattan metrics were just like a little bit better. So for the sake of simplicity, we just kept those out and just kept the Manhattan metrics. So we ran these features in isolation into a decision into a random forest, and they performed 67% accuracy, which was a lot better than how the track features performed. And neighbor skip was surprisingly like the most predictive feature. These are the feature inference scores of each feature graph, by the way. And it was interesting to see that man-app skip was so low. But we're kind of thinking that this is because the types of tracks that a user is skipping, they're very different. So when we try to generalize them into one single vector, it's not really going to mean much. It's not going to generalize it well, so this feature ends up not really performing as well. So we also added contextual data. This is just percent skips, the percentage of songs in the session that the user has skipped, and the pre-song played if the user skipped or played the previous song. These features were just kind of added as an afterthought just to get the, whether or not like a user is just skipping a lot or like, maybe they're asleep and they're not skipping at all. Just to kind of get like, independent of what track they're listening to, are they just skipping a lot? And these features actually, we put these two features into a random forest as well, just by themselves, and they got a 76% accuracy, which was the highest. It was the highest of what we got so far. So this foreshadows really interesting results in our final model. And last, we have the metadata. So whether or not the user has Spotify Premium, of course, this could be important because non-premium users are limited on those skips. And we also have the month and the day of week and the hour of day. So to summarize all of the data that we have in our final preprocessed data set, we have our metrics, our contextual data, the metadata, and then those 29 track features. And we're trying to predict whether or not the song is skipped. So we used different combinations of features to understand which are most important and which combinations produce the most accurate results. So, like before, first the track features were really bad, 50%. The metadata wasn't too much better. Both of these were just kind of as they are from Spotify, as Spotify gave them to us. And when we combined them together, it didn't really improve it by any significant amount. We go to the metrics, 67% is a lot better, and the contextual data was crazy with 76%. When we combined them, we got 78%. But something interesting is that when we put all of these categories together into our all data, we got a lower score than just the metrics and contextual data, which is kind of weird. And we eventually figured out that this was because the track features were in there. So when we removed the track features, our final model turns out to be 78% accurate. So that's just the metrics, the contextual data, and the metadata. So these features were kind of just ruining our prediction. Like, they were worse than being meaningless. Alright, so next. So these are the feature importance scores of the final model. You can see the contextual data just absolutely dominated this graph, which was so surprising. Because we had hypothesized that the metrics would be the most important, and that was the main focus of our research, was to see to understand the similarity between songs and how that relates to what a user is going to do next. So we have last skip and last play being more predictive than av play and av skip, showing us that what a user had just listened to is more important than a generalization of the entire session. Also, as these sessions get longer, those average played and average skip vectors are going to become more diverse and, of course, less relevant. So that could also play a factor in whether it's so low. Another thing is we expected the premium feature to be a little bit more important than it is. Like, you can't even see it there. It's like 0, 0, 0. But this is also probably because the contextual data is implying that the user is premium or not. So if they're skipping a lot, you know they're premium. If they're not skipping a lot, they're probably not premium. So this feature was kind of redundant. So this is our confusion matrix of the final model. Overall, we're better at predicting skips, but we're also predicting plays quite accurately, which is telling us that the model has in fact been learning. But we're not quite capturing the user's mood and preferences. Our predictions are mostly being taken from that contextual data, which is not exactly what we wanted, even though that's what it turned out to be. So our predictions are mostly relying on the user's general skipping behavior. They're not really caring about the similarity of the tracks that they're listening to. Alright, so in future work, we could of course improve our random forest accuracy. We could do this by exploring more within those metrics to make them more important. And we could also use session-specific trees to preserve the session context. So what do I mean by that? Yeah. So for each session, we could train a decision tree on the previous songs with their track data, and then use the final song as the test and just predict on that. So we would make one of these little baby trees, we call them, for each session, and then kind of add the output of whatever this decides into that pre-processed data set, have that as a feature. So it's like an additional way to use the track features that might be more meaningful. And through this, we could also go into further detail on the importance of the track features. Let's go back to the slide. So we could also improve the accuracy by training a recurrent neural network. So a lot of solutions exist using recurrent neural networks, but of course we didn't use that because we wanted to look at feature importance. But we could use these features that we found are most predictive within our random forest, and we could just put those into a recurrent neural network and see what happens. We could also start recommending instead of predicting. We could start to classify all of the songs in a playlist, or maybe just a random subset, and just pick the one that a user is least likely to skip in that moment, sort of altering like a shuffle algorithm to make it more adaptive to the user. If more than one session per user is available, we could start to look at their habits and learn their listening trends. So if someone loves pop in the morning, but they're listening to a lot of sad songs in the afternoon, if they start a listening session in the afternoon, we can start to play sad songs because they're probably gonna they're gonna skip until they get a sad song. So let's just start with the sad song. And of course, the challenge here with all of this is the balance between true randomization and tailored randomization. The worst thing that could happen is if you skip a few songs and then listen to one type of music, and the system keeps recommending you that same exact song in a whole, and you just can't get out of it, and it's annoying. It has to be kind of like it's not there, sort of simulating the time when you put your music on shuffle and every song that you love just plays, and you're in the perfect mood for it, and it's great. So, yeah. Any questions?
So, this algorithm, would it reset if somebody interacted with Spotify? So, if I'm listening to my playlist and their song, I hit next, or maybe I hit a song in that playlist, would the session kind of reset, or would the session kind of learn from the recent interaction?
With the data that we used, I'm not sure if it covered across different playlists. They might have made it so that it was kind of once they changed what they're listening to, they changed from this album to a playlist or the radio, maybe that would have stopped the session. I'm not sure. So the data is just kind of vague. They didn't tell us exactly the specifics of that.
So as the session goes on, the similarities, the songs become more diverse. Is there a length of session for which the predictions are most accurate?
We didn't do that. We should though. But yeah, that would be really interesting to know. I'm sure as it gets longer, especially those average vectors are going to get less and less important. But
It's gonna be, yeah.
it depends on how
There's
similar
only a
the
sweet
person.
spot.
Yeah. Josh.
So, reinforcement learning with human feedback is really popular as of late. So, do you think something like that could apply here? especially like a recommended system.
Yeah, definitely, but I think that reinforcement learning would be best suited for like learning on the user specifically. So of course here the data that I had, it was one session, like you could say it was one session per user. We didn't have multiple sessions, we didn't have like user IDs, it was just session, completely in isolation. But if we were to take this further and if we had Spotify's system, we could probably make it so that they could start to learn on a specific user and fine-tune to what the user wants instead of just kind of generalization of what we did here.
Did you ever notice any directions like advertisement audio in the Spotify playlist or anything like that?
Can you put that in the data? I have no clue.
Is it possible to see how many people skipped based off of a certain artist? So like, let's just say in the afternoon I'm listening to something more like sad, more emotional, and there's a specific artist that might come on. Is it also able to? Are you also able to draw data based off of them not liking a certain artist, and basing it off of those skips as well?
Again, the data they omitted the album and the artist from the data because this data set was like released as part of the challenge, and so they really wanted people to, I guess, focus on the structure of the tracks, and they didn't want any outside information. But that would be a really great feature to add and to have because some people will skip based on what artist. So it's definitely important.
How does it handle if you skip a song and change your mind with that?
So that is in the data. It tells you if there was a forward seat or a back seat. But we just kind of we thought of it as just individual tracks. So we kind of removed that part of the data because in a way it could implicitly tell you whether or not the songs were skipped.
You talked about the challenge, how much data did you get? Where did it come from?
What is it called? It was a conference. It's called Spotify Sequential Skip Challenge. It was a challenge in 2019. I think the acronym is WSTM. But if you Google Spotify Sequential Skip Challenge, it's on things like Birthday. Yeah, I could tell you afterwards if you want the data set. It's like 50 gigabytes.
Was there any type of demographic data on the users, i.e. age or?
No, it was just what they were skipping, what they were listening to, and if they were skipping it or not. Yeah, really nothing on the user.
Just wanted to ask, what's the biggest insight you learned after doing this project?
Biggest insight?
Anything that surprised you?
I guess the contextual data surprised me. It also surprised me how badly the track features alone performed. I was expecting them to be at least a little bit predictive because you have songs that have long endings or really long songs with an interlude maybe in between that people get bored and they skip. And I was also researching skipping trends, how people skip, and it did have some stuff about if there's an interlude, we're gonna skip that. But we didn't find anything.
Yeah, I think the most surprising and frustrating thing was how important the contextual of just whether the user was skipping and whether they last skipped or played, that was not what we wanted to happen. We wanted the distance metrics to really run the day. But it's it's still important. It's important to realize, no, that is really critical and you're gonna have to improve the metrics if you want to gain traction there, so.
What type of tools did you use to, kind of manipulate your data, to look at the data? Were they third party, or did you write some of your own tooling?
Yeah, I wrote all of it myself with Python, using pandas, and data frames and stuff like that. So all open source. Yeah, technically, don't look at my
Yeah, so your comment just a few questions ago about the size of the data set made me think, I think you said you were only using 200,000 of the sessions that were available, and so much of the work that's being done right now around machine learning and AI is based on these just ginormous huge data sets. And so do you have an idea of how much better the algorithm would have been if you had been able to use the entire data set, or like would it even have been better? Is 200,000 enough?
It definitely would have been a lot better, because something I noticed like kind of last minute was that the data that I had, so the time and the dates, those features were kind of ruined because the data was all in like the same 2 months. So it really wasn't varied with that, and so that's kind of like our main reason why we think that was performing so poorly. We're not sure, but it definitely would have been a lot more accurate, I think, if we had used like 130 million sessions.
I know you just said don't open your code, but did you put it out in public anywhere that it can be viewed?
Yeah, it's on GitHub. It's on GitHub. Find a way to like send it, I'm sure how though.
Let's give it one.
I don't know how to get it out to all of you guys.
Is it on LinkedIn?
Yeah, well, maybe we could.
You drop a link.
All right, once you guys get that link together, give a big round of applause.